Welcome back to High Performance Computing, the practical lecture 2.1, the second part. In the first part, we had our first MPI Hello World application, and this was basically a valid C program, but we added a couple of statements, which was the MPI init, the MPI finalized, to determine the parallel region, really, where I can do MPI operations. We included the MPI header, so that the functions of MPIs are, of course, known. And then the first example really was to understand that the same source code will be executed a couple of times. And a couple of times refers now to the amount of basically cores or even number of nodes, as you have seen, that are put in the job script. So basically the application is independently programmed for the number of cores. I can do it with 4, I can do it with 8, I can do it with 12. It will be in the job script to basically, change over time. And we have also seen, in a way, it's a bit sad that we don't really use messages yet, right? So why we should do all of these effort? MPI Hello World was, of course, just to show you a little bit that every application that I execute knows itself, being basically a specific rank that we get out of the MPI com rank information. And then I also know how many are there at all in the space of the communicator, which was then the MPI com size. Also in later lectures, we will understand that we can create our own groups, so we don't have to use MPI com world all the time. But this captures really the essence that at least when we have these different applications now executed on 4 cores, they know basically that they all exist and know that basically they are one part of a bigger applications with 4 cores, with 8 cores, with 16 cores. There are limits. Of course, when you do SBatch several times, let's say with 4 cores, it's different applications. All of them have 4 different cores, but it's not that these 4 cores then can communicate with the other 4 cores or the other 4 cores, right? As soon as you have this SBatch and applications will run even at the same time on the cluster, they are, of course, limited by the number of those that we have in the SBatch script, which is 4 in our examples. That is important already to understand. Again, we had this head idea, no messages, which is for MPI a bit strange, because we learned also MPI stands for message passing interface. Hence, the more elaborate example we had in the first part was then the ping pong to understand this program. Also from the way how you would do this with point-to-point communication with send and receive. This is, of course, something where we also then reflected on the conceptual lecture again, that every ping needs to then basically also receive by someone. And this someone, which is another processor, needs to be ready to receive the ping, right? We need, so to speak, an in buffer coming in, or someone who has the ball analogy. Just, basically think about it. If you throw a ball to someone, the other one hopefully is ready to receive the ball. Hence, the source code was quite interesting that we looked at. It was the differentiation of 2 cores using the rank information, no surprise. So if rank 0, then start the ping. And if basically rank 1, then be ready to receive the ping, hence the send and receive. And of course, this is just the ping. We said we also want to basically do also a pong, and then basically the roles have been changed just to the idea that then the rank 1 was doing the pong, initiated, and then over the wire it is going. We have the status information, if you remember. But then, of course, the pong is just the sending of it. We should be having the rank 0 also ready to receive the pong. Hence, a little bit ping pong, a very simple application, but it captures really the essence of the MPI point-to-point communication. And we want to build on that in the way that we have now much more powerful applications, larger applications, which require maybe the interaction of very many processors. Let's say, for instance, all of them that we have available in order to broadcast some data, in order to perform more message exchanges. This should be, however, still straightforward. So what I don't want to do is now do a for loop and say, well, all the processes involved, please send, receive, send, receive, send, receive, right? For the number of processes. This would be quite elaborate for the for loops. So hence, the MPI collectives are not only a way to basically program that much more nicer, they are also inherently implemented to be much more basically high performance with tree-based structures and so on. So basically, I always would say this is important to realize that we have MPI collectives and you should use them. Don't use for loops and then send receives all the time with all the involved processors. Or you create your own communicators if it's just a part of the application. Usually you can find very interesting ways how to use the MPI collectives. So this kickstarts a little bit our second part, as it is a practical demo, and we have learned already a lot about broadcast, gather, scatter, and reduce that you see here. That's a broadcast one to all. Here, basically scatter an array away to all the other processors, or basically gather them again, and reduce, which was always with some interesting, small operator. This is what we already know, and we also had in the first part the MPI com world. So hence the second part will be now focusing a little bit here on the idea of using a collective operation. And this is a little bit different. So we continue here, as in the first part, we actually now on the Uturn cluster already logged in. So we leave the ping pong example. It was quite interesting, still very simple. And go to the broadcast example here, where we remove the executable shortly, and just go into it and see now a little bit the source code of a very trivial example again, but this time using a collective operation. And the collective we're going to use is broadcast. If you remember, that was giving one data item to all the others. And with the way how this is now basically implemented, we see here an MPI header again. We see the MPI init, the MPI finalize, which makes sense usually to start from, always basically integrating this. Then usually it makes sense to have our com size and com rank also basically very close to the init programmed. What's now different is a little bit the idea what we want to have in logic from the application. So it means, in other words, we will initialize some, let's say, buffer only for some parts of the applications which are run by the rank 0. Hence, this one here, this part of the application will be only run by rank 0, right? If rank, which I get out here, is like what we call the source here, because we later want to use this basically also for sending it out from our rank 0 to all others. This is the only one where I do a for loop and basically initialize each of the different buffer positions here with the for loop iteration value. So in other words, when I'm rank 1, 2, 3, I will not execute this and the buffer will be not initialized. This will be an important part because otherwise, when I now later go through it, you see here, later I want to just give out the buffer and you see there's no difference to any rank, right? This is executed by all. Again, for the understanding, this part of the application, if rank equals source, in other words, rank 0, then initialize the buffer, then do the broadcast, which we will talk about in a moment. And once you have done this, then we want to give out from everyone the buffer. So let's assume we have this, let's say, executed by 4 processors. We would assume that we now have basically this loop from the buffer, which is size 4, basically the values of a buffer 4 times, right? So given out. Since this buffer is not initialized only for rank 0, we will use that as a control, so to speak, if the buffer was really initialized with the iterations of the for loop. Otherwise, there would be wild values. And basically, this then brings us to the broadcast operations. I want now that this initialized buffer, right, is sent, and you see that here, the buffer is sent in the amount of count, which means there's basically 4 integers, which we assume, right, from the memory space, from the source, which is our rank 0 that initialized it, to the MPI com world communicator. Hence, you already see a difference to the basically point-to-point communication, right? We don't have a destination, particularly in the terms of rank. We just say everyone in this particular communicator, which means the collective idea. right? So, and this is what it shares with the gather operation, with the scatter operation, the reduce operation. Obviously, they have different names here, but they all will operate under a certain world of the communicator. And this is obviously not only the MPI-COM world, you can create your own ones, as I was alluding to earlier. Important is also that you see we kind of specify a memory buffer space, which is pointed to here, and also specify what is going over the wire, count of 4 integers we assume. This is of course also needed if you think about that we now basically also have the other processors that need to know what to expect, right? This is not basically hard-coded here. In other words, nobody is doing a receive because it's automatically in the broadcast, right? So to help us basically as programmers to have a very simple operation, you see it's very powerful. With one line, I basically can share information from one rank to all the others. And I don't have to care about all of the different elements. One way of doing it wrongly would be doing a for loop here, and then rank 0 will execute this for loop with 4 different destinations, with all the different destinations of all the other processors, or 3. If you think about 4 processors at all, the rank doesn't need to get it. It has already the information of the buffer, but now we basically want to set it to our others. So we would have a for loop over all the processors and then send receive from everyone. It would be quite more lines of code, at least 5-6 lines of code to do that. Here, this is the beauty of the collective operations. It is very nicely encapsulated in this operation, and we don't have to care about it. Obviously, we should check it, and that's what we want to do now, that we really received the buffer, right? So let's come to more demonstration of this. We do the module load as you know already with GNU Open MPI as an implementation, just to get it into your mind. It's probably still inside and loaded, but I still do this every time to make you understand that this is quite a key. For convenience is -O, so compilation was working nicely. So we have an executable here. We learned that this PWD print working directory gives us a location. This location is important, of course, for the submit script that we have, which is then here. And that's the location. And then the broadcast was the executable that we want to do with MPI run. We have the same modules. And here we determine now, let's use 4 processors. We elaborated on this N a lot in the first part, so I don't talk about that right now very much. But we will change this a little bit to some other ideas to understand a bit more the idea of, again, number of nodes versus number of cores. But in the initial example, we now add specifics, and what we expect is that we have 4 processors that are actually now executing this. And we see it's very quickly already completed again. It's obviously not really the biggest source code, so we would expect that the outcome will be coming in very quickly, right? And we see that here a little bit. Look into the Slurm, and we can prove with this that basically not only the source that is giving out and executing now the print out of the buffer, also the other processes that have been there are giving out the output. And with this, basically, we can prove there was really, again, the broadcast working, because otherwise, at least the other 3 processes would have a buffer that was not initialized. So it would be wild numbers. Here we would have, let's say, a very nice view that the for loop was working in the buffer. And on top of it, the broadcast has sent this buffer information to all the others. Right, so then we also learned in the first part, we can always do this interesting command called scontrol, and then you can show with this particular job ID in mind the information, how much it was running. This may be always good to do at the beginning, at least to understand how many CPUs were really used. You see it's still one number of nodes, that's fine. And to connect this, let this simple example now a little bit to the practicalities of HPC systems, we should view this a little bit again. We talked Uton had these 4 compute nodes, 2, 0, 2, 1, 2, 2, 2, 3, as we discussed, and Uton itself was just the login node that actually usually don't really count as a node, because the login node is not for computing, as you learned already in one of my earlier lectures. What we also learn here is basically that every node has 12 cores, which is also interesting for us here, basically described in this 12 core. system, and then basically has a 2 times CPU on this. And this is something what we want to explore now. Thinking about what is really true, how many cores we have per node here. And do we see this in the job outcome, right? Because we have here 2 times an Intel Xeon CPU that already gives us a hint, basically, how many cores there could be in the system for one node. And as we have 4 nodes, of course, we could go quite in some dimension of using more and more cores. But here we want to think when we cross a boundary of a node and how we can realize and see that now when we basically ask for resources. Obviously, we have to go to the job script for this. And we'll see when we do now n equals 4, obviously that's in one node. When we go now and we'll execute the same on 12 cores, basically we assume that should be not a problem. Basically, we have learned there are 12 cores. So let's see what happened. We also basically expect with this example, there would be 12 times now the output, right? This is now important, if you remember, and this is the beauty also of the source code that I want to show you again in the broadcast here a little bit. Remember, this was now not really programmed towards 12, towards 4, towards 10, 12 processors, nothing, right? It's independent. What is of course hard-coded here is that we have 4 times always an output of the buffer. So the buffer length, if you want. Now what we expect is now executing this, and I think the job is probably already done again. You see that here is now with the second output we have. Basically, we should see that there's much more output. The size already alludes to that this was probably working quite nicely. So let's see this, and you see 12 times, no surprise, the buffer output, whereby only the rank 0 was basically initializing and then basically sending this information to all the other ones. You see also, because there's so many processors now involved, that it's not really deterministic in the output writing, but we seem to see still no strange numbers. So every processor could really wrote the output. And when we do now the S control of this particular job ID, we will probably see also no surprise with 12 cores. We don't expect that there should be something strange happening. We are still asking for 12 CPUs or cores, and we are inside the 2.0 node, right? So this is important now. Also remember what we talked here, 12 core. So to see a little bit, explore the limits of this, it would be quite interesting to understand now what happens, for instance, when we just want to scale higher and maybe do 24 cores, right? Because now we probably touching some limits. We will see that when we now execute this, there would be obviously much more outputs, much more processes involved. Not a problem for us. You also see I don't touch the source code, right? The broadcast operation, everything in this broadcast C operation is still the same way I was programming before. All we did is now the number of cores changed. And basically by submitting this, you see the new one is already completed as well. So we assume that this output file should be much larger because there is a double amount of processors writing, which is basically also reflected here in the size of the output. And if we more it, I guess you can get the story. It's probably the same. You see more even here from all of these 24 processors. Now, interesting for us would be also to understand now what is the node situation, right? So if we want to have some details, so again, the usual show job ID minus DD, and then the new job ID we have here, which is quite interesting because there are also no surprises for us. The number of CPUs is 24, and we have a compute 2.0 node. That means we stand still within the node and explains to us also what's standing here, right? So we have 4 nodes, and each of those basically have a 2 times Intel Xeon CPU with 12 cores. Hence, with 2 times the CPU, which everybody has 12 cores. So that means 24 cores per node is available. Now I have 4 nodes, so I can go up. Let's say 24 cores, I go 48 cores and then involve 2 nodes. Also, let's see what happens then to prove that a little bit. You can use any other one, but for simplicity, we can, for instance, use here just 25, which from the source code perspective is no big deal because the source code remains the same. We can S-batch it again. It will be quickly analyzed because it's also just more or less a very trivial application again, as we know. But it clarifies again that with 12 nodes, we were standing within a node. With 24 cores, we were standing in a node. But what's happening now with 25 is something what we're interested in. Let's see first if we get proper output. The jobs seem to be completed. It's also a bit bigger. That means there's probably one processor more involved, as we also requested. And the output is the broadcast worked. But what is now the idea of the S control information? When we do the job ID of this job that we just looked at, which is the 74. Here you have suddenly now no big surprise for us, but we kind of were thinking about these lines because we asked for 25 CPUs. We know from this information 12 cores per CPU, which means then with 2 CPUs, 24 per node. So when we want to have 25 CPUs, we cross the boundary. You see nicely that the scheduler just does that automatically, right? I didn't ask for 2 number of nodes, what you see here, but we automatically got then 2 nodes because it's now basically on the different compute nodes that we basically can understand better here on the U-turn. We are basically on compute 2.0. There are just 24 available, so the cluster automatically schedules us to the next node basically and occupies 1 processor there. That's the beauty of scheduling. So this is all automated. You can actually fine tune this a lot with number of nodes, know how many number of processors you want to have per node, because this also reflects a little bit to memory availability. And for instance, right, when you have memory bound applications, maybe you want to have not all the cores working, but you need the node memory really, basically to have a memory intensive problem computed, and everything should fit into the memory. So there are different ways how you allocate this. And I think this is not anymore an introductory topic then. This fine tuning of memory will be quite an advanced topic of HPC. But here at least you got the message that with a simple job script, I was able not only to scale the broadcast operation, and this with independence of the source code, right? It was basically automatically scaling up because more and more processors were assigned to the MPI COM world. We started with 4, then 12, 24, and then 25. They all were in the MPI COM world, one after another, of this application execution. That's how it scaled. Everyone in this MPI COM world was basically receiving the buffer information with the broadcast operation, while only rank 0 in all of these executions were initializing it. So that's pretty clear. The other thing you learned is then basically, even if we touch the boundary of a node, right? This is now important. We were on 2.0 as a node, and there were not enough CPUs available, just 24, because we have a 12-core system times 2. That means we have to go to another node, and this is also what the scheduler was doing for us. And this helps, of course, that the scheduler is a very good tool for us, especially if you think now that not only me is executing this, but also many students in parallel working on their assignment right now. Hence, in the future, when you basically do QStat, you hopefully should see many different usernames when assignment 1 is running. And then you will also see that sometimes you have to wait. Not everything will be directly completed, because essentially it could be that there's no space on the cluster. You can imagine when everybody would now ask for 25 cores, we have just 4 nodes. And if this is done by many students, we're running quickly out of cores. So what the solution is, of course, you will be put in a batch queue, right? So you wait until basically the next slot is available where 25 CPUs, for instance, are available. And this is a multi-user idea, and that's why it works quite well. In an automated fashion, you don't have to think about which of the cores you allocate, when basically is your time. The scheduler takes care of all of that and also assures that your MPI application is actually distributed on these nodes and can work with this and the scheduling job script. Now, this was already, I think, powerful information. And to go back, obviously, I put many of these elements I just talk about here in the slides for reading, more or less like a script, where we have the rank buffer initialization. When you do this in assignment 1, obviously that becomes much more into your mind. The difference again between rank 0, rank 1, 2, and 3, right? Only rank 0 is executing this. So basically that's why the buffer is only in one application execution initialized, not in rank 1, not in rank 2, not in rank 3, but as the connection here suggests, the broadcast operation will use this connection, let it be InfiniBand or whatever, in order to distribute then the buffer information. And this is missing here, so we add this in the next, where we then use just the broadcast operation, and this will make sure to reach all the different cores here in the MPI COM world. And you can see that this simple really idea of a, if you want, of a, very simple operation like broadcast is implemented in very cutting edge parallel support vector machines as an example here, where we use that in land cover, basically classification with an AI algorithm called the support vector machine. We have a parallel version of this, which also uses lots of MPI operations in order to differentiate then essentially the different classes, learn first basically from some training set, and then basically with a test set then also is able to classify the different parts of land cover from a satellite image. You see here a little bit the water and different parts of buildings. So hence, even in really very good, let's say, and very powerful application, you have still the simple idea of broadcast. But what we also saw in the history always as parallel programmers is when you work with domain experts, here, for instance, with AI experts, and we took the code of PSVM from the SourceForge original one, you look that people have actually implemented these strange ways of communicating with the for loop I was talking earlier. So this code was an example where actually people are very good, let's say, in AI algorithms, what they should be, but sometimes people that are specialists in this particular field, let's say AI, are not the specialists in parallel programming. So what they did at that point in time was, interestingly enough, a for loop and then send receive to all parts in the communicator instead of just using collectives. And this is something what we will see more and more the more you dive in the field, that we need experts from different areas working together on one problem to make it really high performant. We have this incredibly often that domain experts in chemistry, in physics, really need to work with the computer scientists that understand parallel programming very well in order to get the best performance possible. We have so-called performance analysis programs, which will then indicate these elements and indicate these problems often. So much only also for the practice. If you go into this field, still the PSVM is a very good program. We tuned it with our expertise in parallel programming and are still very grateful that PSVM exists also from the original authors, which have been the experts in AI to really provide their good implementation. All what we did was really do a better MPI if you want, and then scaling a little bit better. So assignment 1 will have this again for you to experiment, and you should also use another collective. So I just summarize here what you have seen. Essentially from me demonstrating, we had the fact of the 4 processors, and we basically don't need to change the C code, which is important here, to 8, 12, 24, 25 processors, something you also saw. And automatically we were also going over the boundaries of a cluster. If you remember, we had not specified capital N, but automatically this was activated because we had 25 cores where U-Twin only basically has 24 per node. This is 2 CPUs we were talking about. So essentially this connects a little bit the practical demonstrations here with the idea that I basically was demonstrating before here in the slides and so on. So it's basically the same material. The remainder of the last couple of minutes, I want to basically show you a little bit another part of scheduling. And with this, a key functionality in HPC, which is related to the so-called wall time, or your time of the application it takes, and a very interesting wording, which is called run against the wall. This is a loaded statement. Think about you maybe running a job or an application for 3 days, and then suddenly the scheduler says, well, you specified the time and actually your job is just stopping, right? And so you executed it for 3 days, but in a way you probably need 4 days, but the scheduler just gives you 3 days, for example. And then we talk about that the application, a little bit like a visual interpretation, is, you know, maybe simulating the boat over the river, all the physics involved, and then suddenly the scheduler says, sorry, you indicated just 3 days, so I stopped this job here. And the physics maybe, or the application maybe not completed. So we simulate this behavior with some sleep, so that we basically don't do hard physics here, but just have a hard-coded sleep, which we can basically steer with a number of, you know, seconds involved out of the only standard library that we include here. So let's go to some practical basics of understanding a little bit more this wall time, which is really an important concept as well. For this, I have another example with sleep, which is the final example for today, but capturing a little bit the essence now of the idea of why we basically have 2 times now this sleep parts / also the wall time. So here we have now 2 steering mechanisms, and it's important to understand this. So let's go to the first one. Here we define now that we have basically sleep seconds, a program that should sleep for 180 seconds, which are basically then 3 minutes. We have the typical idea of init, comp size, rank, finalize, what we had before. All what we do now this time is no basically big ideas of you know, sending messages and so on. Obviously, all what I explain now is also really affecting those applications. But here I want to highlight the idea what happens if you basically now have this sleep, so long running job, but I will make the job script so short time that we are not able to fulfill this sleeping of 3 minutes, right? Let's see. So when we have rank 0, we just give that out basically for the one processor, how many sleep seconds they are. So we expected a little bit the output to understand how many sleep seconds we asked for. Obviously, as it is hard-coded here, we need to compile it, right, to be effective. If I change it here to 120 or 60, 1 minute, 2 minutes, etc., I always need to compile, right? This is, of course, now hard-coded. It's not scalable, as we have seen in broadcast, just to the number of seconds I have somewhere else or in the wall time. This is hard-coded, which should just reflect some physical, you know, parameters to be computed. Whatever it is, it simulates that the application is busy. We talk about it sleeping now and awaking now, but basically what we fake here a little bit is that here's hardcore physics computed, lots of computing time, 3 minutes, something where the application is very busy, even if it's sleeping for us here. But, you know, to game, usually that should be some hard physics computing. As I said earlier, we had now this 180 seconds hard-coded. Right, hard-coded means for us we have to do a modulo, do open MPI and then compile it. That is basically our Hello Sleep C program with the convenience of saying it called Hello Sleep. And in our directory of 2023 in the Hello Sleep, hence we also should include that in the job script, which you see here. We have the same location and then of course also the same executable. I include here N2. This is not so important. Much more important is this fellow, right? We have here a wall time specification of 0, 0, and 20, which says 20 seconds, so and so many hours, so and so many days. It's basically something that you see here on the slides, hours, minutes, and seconds, not days, sorry, of course, seconds, minutes, and hours. What you want to specify in the job description here, also what we have here in this particular demonstration. So what will happen now if I do this, right? I basically submit the application, which I asked now in the job script should just be 20 seconds. Now, the problem is we specified 180 seconds of sleep in the application, right? So what's happened now is this application is just starting as nothing else was happening. It will run into the sleep. and will execute the sleep now 180 seconds. However, the scheduler has a full power of the system, right? So basically you would say that's the overall manager, the CEO of the cluster. I can do what I want. And the Slurm cluster manager got the instruction and say 20 seconds for this particular job. Hence, what we can expect is that instead of running 3 minutes, this job might be still running. And we see that 20 seconds is always a little bit, it takes a bit longer with the scheduler to get the up-to-date information, to distribute the job and so on. But overall runtime would be probably not 3 minutes, because the scheduler has to send a message, and this is automatically done by the scheduler, to this particular application. And something also that we can see and can realize, that you basically were running against the wall, you have to stop, right? So instead of 3 minutes, you have just 20 seconds. Of course, it was our fault in a way, right? Because we specified just 20 seconds. That's not a good idea if you have a running application of 180, seconds. Hence, in a way, that's of course our way of saying the scheduler, how long do you expect to run? With this information, the scheduler can of course then go back to his overall schedule, which I showed you a little bit also in the slides here, right? If you remember, we discussed this in the earlier lectures about Slurm. These are all different people with all different applications across one cluster called jewels. It's not our Uton, obviously a much bigger one, but it helps this Slurm scheduler now to see, can I backfill the job? Where and when I can execute the job. So you see all of these jobs have a certain period of time scheduled for, because basically they have the wall time. And basically this gives the scheduler then an overall picture of all jobs and can optimize this a little bit to different scheduling policies, and then optimize the, let's say, run on this application, on this particular cluster, really in a way that it's, using the best resources possible. And let's look how this practically look like when we now have hopefully the output. So UStat at some point in time was ready. Sorry. So completed basically. And then let's look into the output, which is unfortunately now for us probably not so optimistic, because there was something wrong. And you see that here a little bit, right? So we're starting and saying one of the processors going to sleep, the other goes to sleep. We have a power problem programming here, very beautiful. But what you see also, compute 0 canceled the job due to time limit, which was, of course, us being, let's say, not so clever here to just specify then basically this amount of time. Hence, when I now change this a little bit, and let's say I would say now, for instance, I can ask for 3 minutes, put here 3 minutes in. And of course, this would be important to save. I'm not sure exactly, there was some error in saving. 3 minutes we want, not more. Okay, so this is a wall time now, which would enable us to execute it. For simplicity, I also want to show you again that we can, of course, speed up the job a little bit, because we're also going toward the end of the course time. So let's go into the Hello Sleep C job, and we want to sleep seconds, really just 60 or so, 60 seconds of sleep. So it means we ask for 3 seconds, but the execution will be just 1 second. And we should forget, because we changed hard-coded the source code, right? We have to recompile it. The module load should be still in. So basically I don't do this, but I have to recompile now, changing essentially the executable also from 180 to 60 seconds. In combination now with the job script I was just changing, right, to 3 minutes, we believe now that the job has time enough to finish when we dispatch it, so that we basically don't get this information that we got here, that the job has to be terminated. And this is an important factor, again, influencing scheduling. That's why it's important to understand a little bit the wall time. Now here on the Uton cluster, as a teaching cluster, play around just among us as students and professor and so on, that is not a big deal. You can still execute without this wall time. It will be scheduled and so on. It just take away the message if you go to larger systems, to real production systems in your practice. when you do, in a job or so, then basically you have to specify this much more clearly, and just means also you have to know a little bit what are the runtimes of your application. So you have to experiment with this a little bit. Have you done some wrong stuff on this? Don't worry. What I also didn't show you before is that you can cancel job. In other words, you can terminate jobs again. Let's say you have specified some wrong wall time, and you realize that you can also every time cancel with a job ID, and then it will be not executed. Obviously, you have to be very fast. If it's a toy job or a very simple job we have just learned, it will be very quickly finished. Then, of course, your cancel is a little bit too late. So let's see a little bit what we're coming out of the second operation here. Now, basically, that is the output of the second job. And you see we are awake now. Both of those, they didn't got the scheduling interrupt, as we would call it, to stop, because we basically didn't reach the wall time, right? We had 3 minutes. We comfortably, after 60 seconds of sleep, we're finished. And with this is exactly what we wanted to expect here. And that's already all basically I wanted to leave you on the table here for the second part of this lecture, practical lecture 2.1. MPI is very powerful. It has many operations, but what I demonstrated to you today was more or less really the key essence of point-to-point communications, of collectives, of the wall time, scheduling scripts, the scalability of the applications independent from programming, more via the job script. And we will come to lecture 3 very soon to really understand a little bit more how we do domain decomposition, parallelization, but this is what we have the next time. So talk to you then.